Good morning, students. Today we will start a chapter that is dual nature of matter and radiation. In this chapter, as the name suggests, is dual nature. Dual means both. That is the particle nature as well as the wave nature of the radiation. In the previous chapter, that is in optical part, wave optics, we have studied the wave nature of the radiation. And in this chapter, we will study the particle nature of the radiation. And then we will conclude at the last that the radiation has both dual as well as wave nature. That is why this chapter, what the name of this chapter suggests. Similarly, the matter, wave nature of matter. And in this chapter, we will also study the wave nature of matter. Now, first of all, we will study the topic that is electron emission. We know that in case of metals, there are free electrons. Suppose this is a metal, some conducting material, and in this conducting material, there are free electrons. These dots, they represent here the free electrons inside the metal. Free in the sense means before forming the metal, because we know that metal is formed due to large number, due to the interaction of the atoms. When the atoms are not, when a particular atom is not in interaction with some other atoms, then these electrons are bound with with the nucleus of this atom. But when these atoms, when they come close to each other, so they interact, these electrons interact with the nuclei of the other atoms or with the electrons of the other atoms. With the result, the valence electrons of these atoms, while forming the metal, they get detached from these atoms. And they are not now bound with a particular atom. In that sense, we call them as free electrons, which I have shown them with dots. And rest, these positive charged kernels, this is the nucleus. This is the nucleus, which is positively charged, along with the inner electrons. Because the outer valence electrons that get detached and that is free to move within the metal or within the specimen. So the nucleus along with the inner electrons, that is known as the kernel, and we say atom as a whole is electrically neutral. But when the valence electron get detached from it, the positively charged nucleus along with the innermost electrons, this together is known as the kernel, which I have shown by these circles with positive charge. These circles with positive charge, these are these kernels. And the electrons within the metal are free to move. They are free to move, they are moving within the metal in the same way as the gas molecules are moving in the room because of the thermal energy, because of the temperature, because these electrons, because the thermal motion, they are in motion, they try to come out from the metallic surface. One is the electron, when it reaches to the surface, when they reach to the surface, they try to come out from the metallic surface because of the attractive pull due to these kernels, because of the positive charge of these kernels, because when these electrons, thermal energy ki wajah se, they have a tendency to come out from the metallic surface. When they reach to the surface, because of the attractive pull due to these kernels, they can't. They are not able to come because there is an attractive pull between the kernels and those electrons. So therefore we can say these electrons, they try to attempt to come out from the metallic surface, but because of the attractive pull of these kernels to these electrons, they are not able to come out from the metallic surface. Thus from this we can say, in order to say that if we want these electrons to come out from the metallic surface, then we had to supply some additional energy to these electrons, to the metallic surface, to these electrons, so that they can come out from the metallic surface. Thus, the minimum energy that is required, the minimum energy that is to be supplied to these electrons so that they can come out from the metal, that minimum energy is known as the work function. It is the energy, external energy which is to be supplied, the minimum external energy which is to be supplied to the metal surface so that these electrons just come out from the metallic surface. That minimum energy is known as the work function, and it is denoted by phi naught, and is because the value of the work function is small. For example, in case of alkali metals, for example cesium, the value of work function is 2.14 electron volt. Similarly, for potassium, it is 2.30 electron volt. So we measure this in electron volt because this energy is the energy which is to be supplied to the metal so that these electrons will come out. That is very small. That is of the order of electron volts. Now, what is electron volt? Electron volt, it is the energy gained by the electron when it is accelerated through a potential difference of 1 volt. If we accelerate an electron by a potential difference of 1 volt, at that time the energy as gained by those electrons, that is known as the 1 electron volt. Thus we have seen that if we want that electrons should come out from the metal, we have to supply energy externally. This energy can be supplied to these electrons by any one of the following physical processes. There are 4 different processes by which we can supply this energy, work function energy, to these electrons so that they can come out from the metal. Number 1 is thermal emission. Thermal emission. If you supply a heat energy to the metal and electrons are coming out from the metallic surface, at that time such an emission of electrons is known as the thermal emission. Such an emission is known as the thermal emission, and the electrons which are coming out, they are called the thermal electrons. And the next one, that is known as the field emission. What is field emission? When a strong electric field is applied to the metallic surface so that electrons are coming out from it, then at that time we say such an emission of electrons is known as the field emission due to the field. That means when a strong electric field is applied to a metal, this is of the order of 10 raised power -8 volt per meter. This is the order of magnitude of the strong electric field is applied to a metal so that electrons are coming out. Such an emission is known as the field emission or cold emission. Third is the secondary emission. When a high energetic electrons are made to incident on a metallic surface, these high energetic electrons, which we call them as primary electrons, when they strike the metallic surface, during this strike they may collide with the electrons, these free electrons within the metal, and supply the work function energy. With the result, the electrons will come out from the metal. And those electrons which are coming out from the metallic surface because of this energy as supplied by these primary electrons, this is known as, such an emission is known as the secondary emission. And the electrons so emitted are called secondary electrons. This is known as the secondary emission. Last is the photoelectric emission. What is photoelectric emission? When a metallic surface is illuminated with a light of appropriate frequency, then electrons are coming out from the metallic surface. Such an emission is known as the photoelectric emission, And this phenomena is known as the photoelectric effect. Such an emission is known as the photoelectron emission, and the electrons so emitted are called photoelectrons. These are called photoelectrons. For example, यहाँ पर this electron, this is coming out, and this phenomena, this is known as the photoelectric effect. Thus, we have seen that we can supply the energy to these electrons, to the metals, so that these electrons can come out from the metal. In order to overcome the work function, we have to supply the energy externally, and we have seen we can supply this energy in 4 different ways. Number 1 is the thermal emission, and you will supply heat energy to the metals and electrons will come out, or you will apply strong electric field to the metal, electron will come out, or secondary emission, you made the electrons, high energetic electrons to strike the metal, with the result electrons are coming out. And 4th one is you will illuminate the metal surface with the electromagnetic radiation. Again, electrons are coming out, because in all these cases, the electrons get the energy from these processes and they are coming out. But in this chapter, we are just dealing with this 4th one process, the photoelectric emission. Here we will study the photoelectric effect now in detail. It is experimental, and then we'll see what are the experimental features of the photoelectric effect. We will allow the light to fall on the metal so that electrons are coming out. Then we will see the different effects related to this, like we'll change the intensity, we'll change the frequency, or we will change the potential, or accordingly we will see what is the effect on the energy of these photoelectrons. Now, photoelectric effect. Now, what is photoelectric effect? It is the emission of electrons from the metals when a metallic surface is irradiated with a radiation of appropriate frequency. That emission of electrons is known as the photoelectric emission, and the electrons so emitted, they are known as the photoelectrons, and this effect or this phenomena is known as the photoelectric effect. The photoelectric effect, it was first discovered by the Heinrich Hertz in 1887. Hertz was the first person, Heinrich Hertz was the first person who discovered the photoelectric effect in 1887, while he was performing the experiment related to the propagation and detection of electromagnetic waves. At that time, he found that when the detector plate is irradiated with ultraviolet radiation, the sparking in the detector plate that enhances. And in this way, that was enhanced because of the emission of the electrons. And in this way, this was the first person who discovered this photoelectric effect. After this, there were 2 more persons, that is Wilhelm Halbwachs and Philip Leonard. These were the two persons who studied this, who investigated this photoelectric effect in detail from 1886 to 1902. They have studied the photoelectric effect experimentally in detail. What was the Leonard's observation? Philip Leonard observed that when ultraviolet radiations are allowed to fall on the emitter plate of an evacuated glass tube, this is the emitter plate C and this is the collector plate A. When there was no radiation falling on the emitter plate C, the emitter A, there was no current in the circuit. When the emitter plate of this evacuated glass tube is not irradiated with the electromagnetic radiation, no current was in the circuit because the emitter was not showing any deflection. But he found that when the emitter plate C is irradiated with ultraviolet radiation, when it is irradiated with ultraviolet radiation, this shows the deflection. The emitter shows deflection. That means the current starts flowing in the circuit. Actually, what was happening? The electrons are coming out from the emitter plate, and the emission of these electrons, once they are coming out, they are moving towards the collector plate A because of the electric field which was generated between the plates, which was generated by the battery. Once these electrons are emitted, they are attracted by this because of the electric field which was generated between the plates due to this battery. And this motion of the emission of the electrons causes current in the circuit. As long as the radiation is stopped to fall on this collector plate C, no current also stops. So it means when the emitter plate is irradiated, he concluded that actually when the emitter plate is irradiated with the ultraviolet radiation, electrons are coming out. That means photoelectric emission takes place. This was the Leonard's observation, what he observes. Similarly, Wilhelm Hallwachs, he found that when the negatively charged zinc plate, if we take a negatively charged zinc plate, this is suppose negatively charged zinc plate, when it is connected with the electroscope, gold leaf electroscope, when the negatively charged zinc plate is connected with the electroscope, gold leaf electroscope, the leaves of the gold leaf, they diverges. Why? Because the negative charge that flows, and that because of that negative charge through this conducting rod, they reach to the leaves of the gold leaf, and with the result, because of the repulsion, they diverges out. But he found that when the zinc plate, when an ultraviolet radiation are made to incident on this zinc plate, the negative charge starts decreasing because the divergence start decreasing between these leaves, it start decreasing. And when continuously the ultraviolet radiation are continually made to incident on the zinc plate, at time it reaches when there is zero divergence. It means all the negative charge of the zinc plate, there is no further negative charge on the zinc plate. That means, since we know that electrons are negatively charged particles, actually what was happening, when the radiations, these ultraviolet radiation, when they strike the zinc plate, negatively charged zinc plate, actually these electrons are coming out. When the electrons are coming out, with the result, the negative charge goes on decreases. And when the zinc plate becomes neutral, and we continuously made these ultraviolet radiation to strike the zinc plate, it was found that now the zinc plate start becoming positively charged, because now before this, when it was negatively charged, it means there were excess of negative charge. There were excess of negative charge that were coming out. Now, when it becomes neutral, and after that, when we continuously made the ultraviolet radiation to strike the metal surface, now it is own electrons, those three electrons, they are now coming out. With the result, this plate, zinc plate, becomes positive charges. Again, after that, this shows the diversions, because now the positive charge will reside on these gold leaves, and with the result, they again start repelling each other. And these were the observations made by the Philip Leonard and the Hallwachs. These two persons, they also observed that there was no emission of photoelectrons, no photoelectric emission takes place when the emitter plate of the evacuated tube, when the emitter plate of the evacuated tube is irradiated with the radiation of certain minimum frequency value. That minimum frequency of the incident radiation below which no photoelectric emission takes place, that is known as the threshold frequency. It was their observation. That means if the incident radiation, the radiation which is made to incident on the emitter plate of the evacuated tube, if the frequency of this incident radiation is less than the certain minimum value of the frequency, they have observed it experimentally, that minimum value, they call it as threshold frequency. If the frequency of the incident radiation is less than that, they found that no photoelectric emission takes place. Thus, we can say threshold frequency. The minimum frequency of the incident radiation, the minimum value of the incident radiation, below which no photoelectric emission, no photoelectric emission takes place. That minimum frequency of the incident radiation is known as the threshold frequency. This was the Leonard's and the Halbach's observation. Now, let us see the experimental study of the photoelectric effect. The schematic arrangement, first of all, we will make a schematic arrangement. This is the schematic view of the arrangement for the study of the photoelectric effect. Now, it consists of a evacuated glass tube or quartz tube along with the window W, along with having a emitter palette C, this is the emitter palette C, and a collector palette A. This is the emitter palette C and the collector palette A. Monochromatic light from the source S is made to incident through a window W on the emitter palette, which is photosensitive, photosensitive emitter palette C. And these electrons, one is the photoelectric, when the monochromatic light from the source S is made to incident, allowed to fall on this photosensitive emitter palette C, electrons are coming out from this emitter palette. These electrons are attracted by the collector palette because of the field, because of the electric field between the emitter palette and the collector palette, which is generated between the two palettes with the help of the battery. The potential between the emitter palette and the collector palette, it can be changed with the help of this potential divider. We can change the potential between these two palettes. Thus, we can say that the palette A, that is collector palette, we can make it sometimes positive related to the palette C. With respect to this, with the help of this arrangement, we can make this positive. We can make it is potential as positive related to this, or sometimes we make it negative. When the monochromatic light, when the electrons are coming out, if the potential of this is positive, when we made it is potential positive related to this, then electrons which are coming out from this, they get attracted towards it. If it is made negative, then the electrons which are coming out from the emitter palette, they get repelled, because at that time its potential will be negative related to the palette C. And when the electrons get attracted, with the result, when the electrons are coming out from this, and those electrons, because of the radiation, they are coming out, and those electrons, they are collected by this collector palette. That is why this is known as the collector palette. With this, when these electrons are collected by the collector palette, with this, an electric current is flowing through the circuit. An electric current, because these movement of electrons which are emitted from the emitter palette and collected by they complete the circuit within the tube. And with the result, an electric current starts flowing, photoelectric current starts flowing in the circuit. And that photoelectric current is measured with the help of the microammeter. We are using here microammeter because the photoelectric so produced in the circuit is very, very small. That is why we make use of the microammeter. And the potential difference between the two palettes, across the two palettes, is measured with the help of the voltmeter V. This is the voltmeter V, by which we can measure the potential difference between the two palettes. Now, let us study the this is the experiment setup. Use it to study the variation of this experimental setup. This is the experimental setup which is used to study the variation of photoelectric current with different parameters, like with the intensity of the radiation, we will change the intensity of the radiation, incident radiation, or with the potential of this anode, we will change the potential of the anode related to this cathode. This is also known as the anode. This collector palette is also known as the anode, or this emitter palette is also known as the cathode. So we can change this potential of this anode. Sometimes we make it positive related to the C, or sometimes we make it this potential as negative with respect to C, and see what is the effect on the photoelectric current. Similarly, with the frequency of the incident radiation, or we will change, sometimes we will change this material here in the emitter palette. So today we will see the study of variation of photoelectric current, or we can write it as like this: effect of intensity, effect of intensity, effect of intensity on photoelectric current. Now let us see what will be the effect of intensity on the photoelectric current. If we change the intensity of the incident radiation, what will be its effect on the photoelectric current? How? First of all, let us see how we can change the intensity of radiation. So intensity of the incident radiation can be changed by bringing this source close to the palette C. We will bring this source of light, monochromatic source of light, close to this. Then it means we are increasing the intensity, and we will, if you take it away from the palette C, it means we are decreasing the intensity. In this way, we can change the intensity of the incident radiation. Now, first of all, we will keep the palette A. First of all, in order to see the effect of intensity on the photoelectric current, we keep the collector palette A at a certain positive potential. We will fix the potential of palette A at a certain positive potential value related to the emitter palette C. And the frequency of the incident radiation, we will fix the potential of the anode, potential of the collector palette. We will keep it at a certain positive potential related to the palette C, and we will fix the frequency of the incident radiation. That means we will not change the frequency of the incident radiation. We will only change the intensity. That means keeping the frequency here. First of all, we'll keep the frequency, keeping the frequency and potential of palette A fixed. We'll fix these two parameters. We will fix the frequency of the incident radiation, and we will fix the potential of the palette A. First of all, we will keep the potential of the palette A at a certain positive value related to the palette A, and the frequency of the incident radiation. Now we will change the intensity of the incident radiation. Now when the intensity of the incident radiation is changed, it was found that the photoelectric current also increases. If we increase the intensity of the incident radiation, photoelectric current also increases. Now, if we plot a graph, it was when the plot was drawn between the photoelectric current I versus the intensity of the incident radiation, the plot comes out to be the linear. That means when we increase the intensity of the incident radiation, this is the intensity of the incident radiation, and here we draw the photoelectric current. So keeping the frequency and the potential of this fixed, when we increase the intensity of the incident radiation, it has been found that the photoelectric current also increases. If we increase the intensity, the photoelectric current also increases. When we plot a graph, photoelectric current versus intensity, that comes out to be the linear. That means the photoelectric current, we can write photoelectric current is directly proportional to intensity intensity of incident radiation, or I is proportional to the capital I. This. What does this mean? It implies that actually when the intensity is increases, when we increase the intensity, and with the result we have seen the photoelectric current also increases. Photoelectric current increases means we know that current is measured as the charge flowing per unit time. Per unit time में कितना charge flow होता है circuit में. Now, as this increases, when we increase the intensity of the incident radiation, we have seen that photoelectric current also increases. It means per unit time में जो charge flow होता है, the charge that is flowing per unit time through the circuit, that is Q, that actually increases. That means charge flowing through per unit time in the circuit, that also increases. In other words, we can say photoelectric increase means when we increase the intensity of the incident radiation, actually the number of electrons which were coming out from the emitter plate, that also increases. That also increases. When the number of electrons which are coming out from the emitter plate, when it increases, when we increase the intensity, that means more electrons are reaching to the collector plate. When more electrons are reaching to the collector plate, that means more current, that means more charge is flowing in the circuit per unit time. This is actually what it implies. Thus, we can say it implies that the number of electrons, when we increase the intensity, of the incident radiation, it implies the number of electrons coming out from the emitter plate, number of electrons coming out from the emitter plate increases intensity of the incident radiation is increased. In other words, we can say that the number of photoelectrons per second, emitted per second is directly proportional to the, in other words, number of photoelectrons emitted per second is directly proportional to the intensity. This is what it implies. That means when we increase the intensity, means more electrons are coming out from the emitter plate, which are then collected by the collector plate, with the result that the photoelectric current increases in the circuit. Thus, from this observation, we can conclude that the number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation. This is the effect of intensity on photoelectric current. Now we will study the effect of potential. Now we will see the effect of potential. Here we will change the potential of this collector plate, but here we will fix the intensity as well as the frequency of the incident radiation. We will illuminate the emitter plate C with a radiation of fixed intensity and fixed frequency. And first of all, we will keep this at a certain positive potential. Then we will change the potential of this plate A. We will change the potential of this plate A and see the effects. Now, here we will not change the intensity or frequency of the incident radiation, but we will change only the potential of this. We will change only the potential of this. When we change the potential of this, sometimes, first of all, we will keep the potential of this 0 related to the plate C. Then we will increase when we increase the accelerating potential of the plate C, and we will make the plate A positive related to this. Then After some time, we will change the potential and we will make it negative. And let us see what is the effect on the photoelectric current. When the light of fixed intensity of and appropriate frequency and fixed frequency of appropriate frequency, yani ki the frequency of the incident radiation must be greater than the threshold frequency. When such a radiation is made to incident on the emitter plate, on the emitter plate, the electrons are coming out and we will change the potential. First of all, we will keep the potential of the plate A at a zero potential and we will measure the photoelectric current. It was observed that the photoelectric current is flowing in the circuit. Photoelectric current. We will measure the photoelectric current and we will note down the photoelectric current. Now we will make the collector plate at a certain positive potential with respect to the plate C. It was found that the photoelectric current also increases. When we increase the potential of this, when we make the plate A more and more positive related to the plate C, it was found that the photoelectric current also increases. That also increases. When we continuously increase this also increases, photoelectric current also increases, and it reaches to a maximum value. It reaches to a maximum value, and the current saturates. After that, if you further increase the positive potential of the plate A, photoelectric current will not increase further. That maximum current of photoelectric current, that is known as the saturation current. The maximum value of the photoelectric current, that is known as the saturation current. Now, similarly, if we will keep this, we will make the potential of this plate A, yani ki collector plate, now we will make it negative related to the plate A. What is happening to the photoelectric? It was found that the photoelectric current start decreasing. If we made more and more negative retarding potential, in the first instant we are keeping the we have increased its potential and we are increasing the accelerating potential. Now the potential of this, when we make it negative related to this, the potential of the plate A is known as the retarding potential. That potential that is known as the retarding potential. When we make it as positive related to this, that potential is known as the accelerating potential. When we make it negative related to the plate C, this is known as the retarding potential. When we increase the retarding potential of the plate A, it was found that the photoelectric current starts decreasing. When we make its retarding potential more and more, it was found the photoelectric current decreases rapidly, and it at a certain negative potential, retarding potential of the plate A, where the photoelectric current becomes zero. That potential, that negative potential of the plate A, that is known as the stopping potential or cutoff potential. Now, if we plot a graph, collector plate potential, which I denote by V, and here it is photoelectric current. This is the nature of the graph. This is the photoelectric current versus the collector potential. The nature of the graph comes out to be like this. Now, when we keep the anode potential at the first instant, first we keep the intensity and the frequency of the incident radiation fixed. We will not change either the intensity or the frequency of the incident radiation. But the frequency of the incident radiation must be greater than the threshold frequency, so that the electron should come out, because this was observed by the Leonard and the Hallwork, that the radiation that is made to incident on the metallic plate, so that the electron should come out, the frequency of the incident radiation must be greater than the threshold frequency. Now, when the potential of the plate A is made negative, when we keep it at when the potential of the plate A is zero related to the plate A, C, and it is at the zero potential, the potential difference between the two is zero. It means there will be no electric field. But when we see that at zero potential, and it is not attracting the electrons which are coming out because of the photoelectric emission, because light of appropriate frequency is made to incident, we are eliminating it with the light of appropriate frequency, electrons are coming out. When the electrons are coming out, when the electrons are coming out from this. So some of the electrons are reaching to the collector by itself because there is no field, because this is kept at the zero potential. So they are reaching themselves to the plate A because there are some electrons who have sufficient energy to reach the plate A. That is why this shows the photoelectric current. Even the potential of the plate A is zero. So it implies that the electrons which are coming out from this plate, this implies that electrons are coming out from the plate C with some kinetic energy. Now, when we increase the positive potential of the plate A, when the accelerating potential of the plate A is starting here, when we make the potential of plate A positive related to the plate C, now it will attract the electrons. What we have found that the photoelectric current also increases. Photoelectric current, when we made it more positive, more current the photoelectric current further increases till it reaches to the maximum value. Now, after that, if we make the potential of the plate A negative, we'll make the retarding potential. The potential of plate A is now negative related to the plate C. The photoelectric current, it was found, it decreases rapidly. And it becomes zero at a particular negative potential of the plate A. That negative potential, which I have denoted by the V0 here, negative V0, that is known as the cutoff potential. What does this mean? That means even the most energetic electron, the electron which are coming out from this because of the radiation, the most energetic electron which is coming out, that is also not reaching to the plate A. So this is what, so let us summarize, let us see what are the main points of observation. At zero anode potential, when the potential of the anode is made zero, that is this point, photoelectric current exists. There is a photoelectric current. It means that electrons are emitted. It means that electrons are emitted from the emitter with some kinetic energy. Why? Because when we make the potential of the anode A zero, as I told you that there is no electric field between the plates, because when the potential of this is zero, then this potential of this is zero, the electrons will not be accelerated by any electric field. So therefore, still the photoelectric current exists in the circuit. Means the electrons which are emitted from this, some of the electrons are reaching to the plate A, which causes the electric current, which causes the photoelectric current in the circuit. That is why from this observation, from this we can conclude that the electrons which are emitted from the collector plate, which are emitted from the emitter plate, they are emitted with a certain kinetic energy. Now, observation point number 2. Now, as anode potential is increased, photoelectric current also increases. Photoelectric current also increases. What does this mean? That means the electrons which are emitted from the collector with certain kinetic energy, as from the first observation, which we have summarized in the first observation. That means it implies that the electrons so emitted from the collector, they have different kinetic energy. Why? Because When the potential, let us suppose the electron is emitted from this, let us suppose different electrons, let us suppose for a particular intensity, let us suppose there are the electrons which are coming out per second, let us suppose they are 5. 5 electrons are coming out. 5 electrons are coming out. Suppose the energies, the kinetic energy with which they are coming out, let us suppose that is 1 joule, 2 joule, 3 joule, 4 joule and 5 joule. But when the potential of this was 0, that means there was no accelerating potential which can accelerate the electrons, which can supply some additional energy to these electrons while they are coming out. At that time, only these two type of electrons are reaching at when the potential was 0, because they have that much of energy, kinetic energy, so that they can reach to the pallet A. But these electrons, they don't have sufficient energy to reach the electron. They have kinetic energy, but they don't have sufficient kinetic energy to reach the pallet A. But when, so therefore only these two type of electrons are reaching. That way at that time we can say only 2 electrons in 1 second are reaching to this pallet A when the potential is 0. Now when we increase the potential, of the pallet A, as the potential is increased, that means an electric field is generated between these. That electric field will supply additional energy to these electrons. That is added to these electrons, this electron also. Let us suppose it adds some more energy, 1 joule to these electrons also, 3 joule. Now they becomes now 4 joule when we increase the potential. When the energy of these becomes 4 joule, these electrons now also are able to reach the pallet A. When that means now the 3 electrons are reaching to the collector pallet A. That is why we say the photoelectric current increases. Similarly, when we further increase the accelerating potential of the pallet A, the photoelectric current also increases. That means these are also getting the energy, these are also getting the further energy, so that they can reach to the pallet A. When the potential, at a certain potential, when all these electrons have sufficient energy from the field, when they get, because per second, in 1 second, the electrons which are coming out from the emitter, that is suppose 5. When the accelerated potential, we have continuously increased the accelerating potential, what is happening? That means the number of electrons reaching to the pallet also increases, because that field between the pallets that supplies additional energy to these, to those electrons also, which initially were not able to reach the pallet A. So this is why it is increased. Now after some time, after a certain positive potential, accelerating potential, the current reaches to the maximum value. That maximum value of the current, that I know, that is known as the saturation current, I saturation. That is the saturation current. And now the current is constant, photoelectric current. That means if we further increase the accelerating potential, that the photoelectric current doesn't increase further. That remains constant. That constant value, maximum value of the photoelectric current, that is known as the saturation current. So that is why what this implies, that the electrons are emitted with different kinetic energy. It implies that electrons are emitted from the emitter with different kinetic energy. This is what it implies. When we increase the potential, the photoelectric current also increases. It implies that the photoelectrons emitted from the emitter pallet are emitted with different kinetic energy. This is what it implies. Now the third. Now when we further increase the photoelectric current, when we further increase the collector potential, the photoelectric current reaches to its maximum value. That maximum value is known as the saturation current. What does this mean? It means the number of electrons emitted per second from the emitter is fixed. For example, as I told you, per second is 5. When the 5 electrons are emitted in 1 second, all the 5 electrons are reaching to here. All the 5 electrons are reaching here. Again in next second, 5 electrons, all those electrons are because their accelerating potential is sufficient. That is sufficient, that is enough, which can supply energy to these electrons having smaller kinetic energy. Once they are coming out, they get additional energy from the field. They too are reaching to the collector plate. So that means from this observation, the current becomes maximum. It implies that the number of electrons emitted from the collector plate, that is fixed. After a certain collector potential, photoelectric current occurs its maximum value. Occurs its maximum value, called saturation current. That maximum value is the saturation current. What it implies? It implies that the number of electrons emitted per second from the emitter, coming out from the emitter, is fixed. That means in 1 second it is 5. That means in next it is again 5. It will not be 6 or 8 or 10. Because if it is so, then the collector current should also increase. Fixed means per second, in 1 second, the number of electrons reaching to the collector is 5. Again 5. That is 5. In 1 second it is 5. In next second it is again 5. In third second it is again 5. That means the number of electrons reaching per second to the collector is 5. That is why the current remains fixed. The charge flowing per unit time is 5 electrons per second. That is fixed. This is what it implies. It implies that the number of photoelectrons, emitted per second from the emitter is fixed. That is fixed. Fourth. Now as the potential of the anode A, as the potential of the collector plate A is made negative, the photoelectric current decreases rapidly. Now it is, as is observed from the graph, as the potential of the plate A, that is collector plate, is made negative with respect to plate C. Photoelectric current decreases. Photoelectric current decreases. Now it decreases, photoelectric current decreases rapidly, and at a certain retarding potential of the plate A, as I told you, when we make the potential of the plate A negative, that potential is known as the retarding potential at that time. When we make it as positive with related to the plate C, that is known as the accelerating potential. Now, as the retarding potential of the plate A is increased, at a certain minimum, negative potential. Negative potential, that is minus V naught, of the plate A, यानी कि of the emitter plate A, the photoelectric current becomes zero. The photoelectric current becomes zero. Becomes zero. This is called the stop. The minimum negative potential of the anode A, then minimum negative potential of the collector plate A, where the photoelectric current becomes zero. That potential is known as the stopping potential. This is known as stopping potential. Or cutoff potential. The magnitude of which is some V naught, which I have denoted by V naught. These were the main pointers of observation from this graph, which we have found experimentally. From this experimental graph, these were the main pointers of observation. Now, let us calculate the stopping potential. How stopping potential? Because stopping potential means when we increase the retarding potential of the plate A, when we made this plate A negative related to the plate C, the photoelectrons which were coming out from this at the zero potential, when the potential of this was zero, only, as I told you, only 4 joule and 5 joule electrons were able to reach the plate A. Now, when we make its potential as negative, that means this plate will repel the photoelectrons which are coming out from the emitter plate, because the potential of this is negative and electrons are also negatively charged particles. The plate will retard the motion, of these coming electrons. Therefore, we can say, let us suppose when we increase the negative potential, when we make the plate A as negative related to the plate C, that means it repels the electrons which are coming out. Since at zero potential, only these two types of electrons having 4 joule and 5 joule energies, kinetic energies, they were able to reach the plate A. But when we make this negative, now the plate will repel the electrons. The repulsion is not sufficient enough to stop these 5 joule electrons, but it is able to stop the 4 joule electrons. That is why current is decreasing. That is why photoelectric current is decreasing. Now, when we further increase the potential and when we further increase the retarding potential of this, and when we made the potential equal to V naught, then at that time, these 5 joule electrons, and most energetic electrons which are coming out from this, which are coming out from the emitter plate, they are not able to reach the plate A. They are stopped by this. The most energetic electrons having the maximum kinetic energy, they are not able to reach the plate A. That is why when they are not able to reach the plate A, even these electrons are not able. That is why the photoelectric current becomes zero. This is the reason why stopping potential, this is known as the stopping potential, even it stops the most energetic electrons, photoelectrons, which is coming out from the emitter plate. Now let us find the relationship between stopping potential and the maximum kinetic energy of the photoelectrons. What is stopping potential? The minimum negative potential of the collector plate. The minimum negative potential of the collector plate at which the photoelectric current in the circuit becomes zero. That minimum negative potential of the plate A is known as the stopping potential. cutoff potential. Now let us calculate the relationship between the kinetic energy. Now let us suppose, as I told you, when the electrons are coming out with different kinetic energy from the emitter plate, the most energetic electron whose kinetic energy is maximum, let us suppose that is denoted by K max, is the maximum. Now, as I told you, that when we make the potential of plate A negative, yani ki retarding potential, it repels the electrons. When the photoelectric current becomes zero, we say actually the potential, the repulsion is so much that even the most energetic electrons, and 5 joule electrons, as I told you, suppose 1 joule, 2 joule, 3 joule, 4 joule, and 5 joule electrons are emitted from this. These 5 different types of electrons having different kinetic energies are coming out from this in per second. Now, when we made the potential of this negative, when the retarding potential is V0, yani ki when it is equal to the stopping potential, then at that time, the most energetic electron, because as it is approaching to as this most energetic electron, let us suppose this is the electron with 5 joule, this is the electron having the energy 5 joule. Now, while it is coming out with having a kinetic energy 5 joule, now it starts moving towards the plate A. Now, as it is moving plate A, this will repel. Because of that repulsion, its energy decreases. But still, it is moving with a lesser kinetic energy now. It reaches here, now the kinetic energy is only 2 joule. When it reaches to the very, very close to the plate A, the repulsion is so much that it is not collected by the plate A. Even if it is reaching to the plate A, very, very close to the plate A, but it is not exactly collected by the plate A. It reaches to this plate A. But the potential of this plate is some V0, minus V0. Now we can apply the energy conservation. Initially, when the most energetic electron, which was emitted here, the potential here was 0. And related to this, the potential of this is minus V0. What is the potential energy? You know that what is the potential energy of these electrons which are coming out from this, because here the potential is 0. So therefore the potential energy of the initial potential energy plus initial kinetic energy of this most energetic electron, this must be equal to the final potential energy plus final kinetic energy, as per the law of conservation of energy, because the electric field which we have created with the help of this battery, we know that the electric field is the one of the conservative field, and in case of conservative field, mechanical energy is always conserved. So therefore, the potential energy, you know that the potential energy in the field where the potential is V, the potential energy of the charged particle in the potential where potential is V of charge Q, that is Q into V. So therefore, since the potential of the plate C is 0, we keep the potential of this 0, and this is some V0. So when the potential is 0, therefore the potential energy of the electron is 0, because V is 0. This is 0. Plus K max, the kinetic energy of the electron which is coming out, the most energetic electron, we are talking of the most energetic electron, that is K max. We have assumed this is the maximum kinetic energy of the photoelectrons. And this is equal to, when these electrons are moving, when this most energetic electron, the 5 joule electron, as it is moving towards the plate A, because of the electrostatic repulsion, this kinetic energy is being converted into the electrical potential energy. Actually, because this is one of the conservative fold, because of the repulsion, it is being converted, this kinetic energy is being converted into the potential energy. And that potential energy is equal to the charge of the particle, that is minus E, and what is the potential of the particle, that is minus V0. Because when it reaches to the here the potential is approximately equal to minus V0 plus, and what is the kinetic energy? Because it stops here completely, that is kinetic energy becomes 0. That means final kinetic energy is 0. Or we can write it as, this implies that, or K max, this is equal to EV0. And this is the important relationship between the maximum kinetic energy and the stopping potential. Now, if we know the mass of the electron, if m is mass of the electron, if m is mass of the electron, if m is mass of electron, and V max, it is maximum speed. Maximum speed. Then K max can be written as 1/2 of m V max square. This is the kinetic energy. Or we can write from this EV naught, or 1/2 of m from this. Suppose this was equation first, this was equation second. From first and second, we will get, that means this K max is this, here the K max is this, so therefore we can write 1/2 of m V max square is equal to EV naught. If we know the stopping potential from the experiment, because there is a voltmeter by which you can measure this, and you know the mass of electron, and that is equal to 9.1 into 10 raised to minus 31 kg. That means you can calculate the maximum speed of the photoelectrons. This was how you can calculate the maximum speed or maximum kinetic energy of these photoelectrons. Now, in the next lecture, we will see what is the effect of intensity on saturation current, or effect of frequency on saturation current, and so on and so on. Best of luck.